So now we are giving a function f which is belonging from R till R, where fx is ax plus cosx is an invertible function. Then we need to find the complete set of values of a, which is written here, right? So now, what is the condition for a function to be invertible? So for a function fx to be invertible on R, it must be 1, 1 and onto, right? This is a very important condition that we need to keep in our mind. So now we'll again write fx for our convenience, and we'll use superimposition method not to solve but to visualize what exactly is our function, right? So now let fx be gx plus hx, right? We'll split the function into two different functions again, where gx is ax and hx is cosx. So now we know when we plot a linear function, it is like this: gx is ax, right? Where a is the slope. Then we have hx as cosx. Now when we apply superimposition, we try to plot for gx plus hx. A graph is going to look like this. Okay, so this is a very interesting observation which I just provided for your knowledge, that whenever a linear function and a sinusoidal function are added together, the function is going to look like this, right? Okay. Now let's start the solution. That was just for your knowledge. So now whenever we need to find more about the function fx, our first intuition is to find the derivative so that we can find out more about the function. So when we find the derivative, we find it is to be a minus sine x. Now function, we also know that function is invertible. It is 1 1 and onto. That means the derivative should not change any sign, right? It should not change any sign in order to be invertible. So we know that sin x is from minus 1 till 1, right? So somebody can ask that why I am making it concrete that the derivative should not change any sign. So when I am saying this, that means the derivative can either be greater than equal to 0 or it can be less than equal to 0, right? And when it is greater than equal to 0, function is strictly increasing, and when it is less than equal to 0, function is decreasing. So if I contradict my own statement, I say that let the function be increasing and decreasing both. That means at some value of y, I am going to get two mappings, two solutions, right? Two values of x which give the same y. And when I try to plot it like this, that means my mapping is going to look like this. But but this is not a 1 1 function, right? This is a many to one function, many one function, right? That means this, when we have this condition, our function is not going to remain invertible, right? That means now you understood that why we said this, that derivative should not change sign. Now we know that sin x is from minus 1 till 1, right? Because we cannot do anything for this a, but we can do something for this sin x. It is a variable term. Now we'll check for both cases whether function is increasing and it is decreasing. So when it is increasing, a minus sin x is bound to be greater than 0. That means a must be greater than sin x. If a is greater than sin x, what does that mean? What does that clicks? Because we know that sin x belongs from minus 1 to 1 for all values of x belonging to R. That means if a is greater than the maximum possible value of sin x, right, then the condition 1 will be satisfied, right? So we need a to always be greater than or equal to sin x. So when is this condition possible? That means a must always be greater than 1 or equal to 1. then only this condition is going to be possible, because if a is less than 1, then it will reject this thing, right? That means a is greater than sine x maximum value. That means a is greater than equal to 1, right? So this is our observation for case 1. Now for case 2, when the derivative is less than equal to 0, fx is decreasing, right? That means a is less than sine x. If a is less than the minimum possible value of sine x, then condition 2 will be satisfied. Obviously, so we must ensure that a is always less than the minimum possible value. Then only we can ensure that sine x is always greater than or equal to. That means a is less than minus 1. This is what we derive for the next condition. So now we are not having any specific condition which obligates us to say that our function is strictly increasing or decreasing. It can take any of these values. That means we need to apply a union symbol, right? So finally we can write a function like not function, we can write the range of a like this.